This is going to be lecture 28. So let's write that down. This is lecture 28. And today we are going to discuss the complete response of the RLC circuit. All right. Now, so what we are going to consider are those RLC circuits in which a DC source is now switched on. Okay, and that DC source produces a forced response, and that forced response, of course, doesn't vanish as time becomes infinite. All right, so once again, one has a natural response and a forced response. And let's assume, for the sake of argument, that we are talking about a voltage, any voltage, all right? And so the voltage is going to be of the form, the response is going to be of the form, some natural response of time plus some forced response of time. Okay? Now, we know that the natural response, Vn of t is going to be of the form a1 e to the s1t plus a2 e to the s2t, right? And we know that the forced response, the forced response to a DC voltage source or some current source somewhere, the forced response is exactly determinable. And so I will just simply say this is some V sub F. Okay? And so our solution, therefore, the response is V of t equals a1 e to the s1t plus a2 e to the s2t plus V sub F. Okay, the natural response plus the forced response. What remains now is to determine the coefficients a1 and a2. But what is important to remember in this case is that the coefficients, the constants a1 and a2 are obtained from initial conditions as applied to the total response. Okay? All right? So not just to the natural response, but to the total response. That's an important point. All right. So let's continue. Let's continue along our way. Let's assume we have let's say v at 0 plus. Suppose we know v at 0 plus. Okay, that will give me a condition a1 plus a2 plus vf. All right, so that is one condition. All right. The second initial condition is to be obtained from the derivative of the response. The derivative of the response, dv dt is equal to S1 a e to the S1t plus S2, this is A1, sorry, S2 A2 e to the S2t. All right, remember VF is a constant, so that's plus 0, if you like. And what we want is dv dt at 0 plus, which then becomes equal to S1 A1 plus S2 A2. All right. So we have our two initial conditions. V of 0 plus and dv dt at 0 plus, okay, in terms of A1 and A2 and VF. All right. And what now remains is the determination. What remains now, and let me do it over here. What remains now is the determination of the left-hand sides of the equations for V at 0 plus and the left-hand side of this equation, which is dv dt at 0 plus. Now, one can solve the circuit at 0 plus to obtain V at 0 plus. But how does one obtain dv dt at 0 plus? Okay, well, suppose we know the following. We know that the current through a capacitor, okay, the current through a capacitor is C dV dt. All right. And so if you know the current through the capacitor at 0 plus, you know dV dt at 0 plus. All right. So let's write that down. Therefore, dV dt at 0 plus equals I sub c at 0 plus over c. All right. So, so you can determine dV dt at 0 plus. All right. And consequently, then determine the coefficients A1 and A2 through the two conditions. V of 0 plus is obtained by solving a DC circuit problem at 0 plus, and dV dt is also obtained from that solution of the circuit at 0 plus because in solving that circuit at 0 plus, you're going to determine I sub c at 0 plus, and therefore you can determine dv dt at 0 plus. All right? So let's do a problem. I think let's do a problem and kind of put all of this into practice. All right. So here's the example. And it's a long example because I want to show you how to determine all the properties of such a system. So let's assume this is V u of t in amps, for u of t in amps. I'm going to assume there's an inductor of 3 henries. This is the direction of the initial current. This is the voltage across the inductor. Then I have a resistance of 30 ohms. I'm going to call this current here I sub R, and the voltage across the resistance as V sub R. Okay. Then I'm going to have a capacitor. Okay. Value is 1/27 farads. I'm going to assume this is the initial direction of current. This is the consequent capacitor voltage, V sub C plus minus. And last but not least, I have another 5 amp source here. Okay. All right. So we want to solve for all the properties of this system. Okay. Let's solve for all the properties of the system, by which I mean there are 6 quantities. It's the current through the inductor, the voltage across the inductor, the current through the resistor, the voltage across the resistor, the current through the capacitor, the voltage across the capacitor. Okay? So, let's begin. As we've done in the past, let's start from minus infinity to 0 minus. Okay? So, in going from minus infinity to 0 minus, notice on the left-hand side of the circuit, the function u of t. So from minus infinity to 0 minus, u of t is 0. Okay? So that's an open circuit. All right? And then what we have from minus infinity to 0 minus is the 5 amp source on the right, which means it's a DC circuit. Okay, which means it's a DC circuit from minus infinity to 0 minus. We know the following 2 important facts. We know that the inductor is a short to DC, and we know that the capacitor is an open circuit to DC. So let's draw the circuit at t equals 0 minus. Okay, let's draw the circuit at t equals 0 minus first. All right. At t equals 0 minus, as I just said, for u of t's current source doesn't exist. The inductor is a short, so let me short that inductor, and so this will be I sub L. This is plus minus V sub L. Then I have the resistor. I have the resistor, which is 30 ohms. This is I sub R. This is plus minus V sub R, voltage across the resistor. And now I have the capacitor is an open circuit. Okay, so this is my I sub C at 0 minus, and this is plus minus V sub C at 0 minus. And last but not least, we have the 5 amp source, and that's my circuit for t equals 0 minus. Okay, and so let's now determine the 6 quantities that we want to determine. So if I look at this circuit at t equals 0 minus, I see immediately, and I guess I may as well, let me use, well, let's see, what should I do? What should I do? It doesn't matter. Let me use this. Let me use the entire page. Okay, so now we look at the circuit, and what stares us in the face immediately is that V sub L at 0 minus equals 0, because it's a short. What is I sub C at 0 minus? Again slaps us in the face, is equal to 0, because it's an open circuit. What is I sub R at 0 minus? Well, it's a single loop circuit, for God's sake. So this is equal to minus 5 amps, right? What is I sub L at 0 minus? Well, same thing. It's 5 amps. Remember, the directions are given. So where I sub R is minus 5 amps, and I said this is a single loop circuit, I sub L is 5 amps. What is V sub R? Oops. What is V sub R at 0 minus? Is I sub R at 0 minus times R. And so I sub R at 0 minus is minus 5. So it's minus 5 times R, which is 30. So this is minus 150 volts. And I've got I sub R, I've got V sub R. What's left? 1, 2, 3, 4, 5. Oh, one thing is left only, which is V sub C at 0 minus, and V sub C at 0 minus can be immediately seen if you look at the circuit carefully. Plus minus V sub C equals minus V sub R at 0 minus, and minus V sub R at 0 minus is plus 150 volts. Okay, so here are all the six properties of the circuit. um, at 0 minus. Now we are going to go on to drawing the circuit at t equals 0 plus. At t equals 0 plus, the function u of t is 1. So at t equals 0 plus, this current source of 4 amperes on the left becomes alive. It's switched on at that point. Okay? Another important point is that we know that the current through an inductor cannot change instantaneously, and we also know that the voltage across the capacitor cannot change instantaneously. So let's go on to the next page. And so let me draw the circuit at t equals 0 plus. But even before I draw the circuit at t equals 0 plus, I note the two following pieces of information. I know that I sub L at 0 plus from the previous page is 5 amps. And I know that VC at 0 plus equals 150 volts. Maybe what I should do is, maybe I should do the following. Maybe I should say, since we know, let me put down here IL at 0 minus, which is equivalent to I sub L at 0 plus, and V sub C at 0 minus, which is equivalent to V sub C at 0 plus, equal 150. So I already know 2 of the 6 quantities, all right? But the point is this: I want to draw the circuit at t equals 0 plus. So let me draw the circuit at t equals 0 plus. So at t equals 0 plus, the circuit looks like this. Here is 4 amps, right? My inductor current, I know, is 5 amps from above, okay? And I know that the voltage across the inductor is plus minus V sub L. This is I sub L, we know that, okay? Then I have my resistor, which is 30 ohms. This is I sub R at 0 plus, and this is plus minus V sub R at 0 plus. And then I have a voltage source plus minus 150 volts, right? The voltage across the capacitor at 0 minus on the previous page was 150, so I can replace the capacitor at t equals 0 plus with a 150 volt source, and so this becomes I sub C at 0 plus. This is of course plus minus V sub C at 0 plus, and then I have a 5 amp source over here on the right. And so this is my circuit at t equals 0 plus. Okay, and this is a DC circuit problem. This is a good old DC circuit problem. So I have to determine 4 quantities. So let me determine those 4 quantities. I've determined 2 already. Now let's look at let's look at the left node. Let's look at the left node. Okay, and let's apply KCL to the left node. Well, what KCL says is that I sub L at 0 plus leaving plus I sub R at 0 plus leaving equals 4 amps coming in. Okay? Now I sub L at 0 plus I know is 5 amps plus I sub R at 0 plus equals 4, and therefore, lo and behold, therefore I sub R at 0 plus equals minus 1 amp. Okay, so that's my third quantity. So let's mark these things down this way. This is 1, this is 2, this is now 3. Okay, but if I know I sub R at 0 plus, I also know, therefore, V sub R at 0 plus equals I sub R at 0 plus times R, and let's do this. This is equal to minus 1, if you just calculated above, times R is 30, and so V sub R at 0 minus is equal to minus 30 volts. So that's my fourth property. Okay, now let's look at the right node. Right node. All right. At the right top node, we have 5 amps going in plus I sub R at 0 plus going in equals I sub C at 0 plus leaving, right? So we know I sub R at 0 plus, so this is 5 plus minus 1 equals I sub C at 0 plus, which then turns out to be 4 amps. Okay, so that is property number 5. Okay, and last but not least, can I squeeze it in? Let's see if I can squeeze it in here. Maybe not. Maybe I'll go up here. Let me go up here. And now let me apply KVL to the central mesh. So central mesh, apply KVL to the central mesh, and you see that, come on, yeah, you see that V sub L at 0 plus must equal plus minus, right? So then it's V sub R at 0 plus minus again, V sub C at 0 plus, everyone see that? V sub L equals V sub R plus minus of V sub C at 0 plus, and so this is equal to minus 30 plus 150, and this gives me 120 volts, and this is my sixth property. Where should I put that arrow? Oh, let me squeeze it in here. That's my sixth property. Okay, so I've now solved the circuit at t equals 0 minus. I've solved the circuit at t equals 0 plus for these six properties. All right, but that's not enough. I need 6 derivatives now. Okay, that's what I need. All right, so let's now attack the derivatives. All right. All right. So let's say next we need to determine let's say the derivatives at t equals 0 plus of all 6 properties. All right? So let's begin with what is absolutely obvious. We know the following. We know that the voltage across the inductor is given by L di L dt. Okay? Therefore, this leads to dIL dt at t equals 0 is equal to V sub L at, well, obviously this is 0 plus we're talking about, so let me put a plus here to be absolutely obvious. So V sub L at 0 plus divided by L. Okay, and so I know V sub L at 0 plus, and so this is equal to, where should I do it? Let me do it over here so I can put an arrow somewhere. This is equal to V sub L at 0 plus is somewhere on the left side of the page. Oh no, it's above. It's right above. So it's 120 over L, which is 3 henries. So this equals 40 amps per second. This is property number 1. Similarly, we know that VC equals c dvc dt, and therefore dvc dt at t equals 0 plus equals v sub c at 0 plus over c, and this equals v sub c at 0 plus is on the left side of this page. It's no, I'm making a mistake. Sorry, take it back. Let me erase something. This is I sub c. This is I sub c. Gotta be careful. Okay, it's I, which is c dv dt. Okay, so as I sub c at 0 plus, and I sub c at 0 plus is somewhere on the left hand side. There it is, at the bottom of the left hand side. So it's 4 amperes over 1 over 27, and this is equal to 108 volts per second. So that's 2 properties. I got 4 more to go. All right, let's see if I can squeeze them in here, but I doubt it. All right, let's see. So again, let's go to the left node. At left node, okay, the point here is the following. KCL and KVL are satisfied by the derivatives also. So the same expressions can be used for the derivatives. And so at the top left node, I have the following. I have 4 going in. I have minus I sub L going in, minus I sub R going in, equals 0. All right. Okay. Remember, this is all for t greater than 0. And therefore, if I take the derivative of this expression, I get, okay, should I write down here? Taking the derivative, one obtains, taking the derivative, one obtains 0 minus dIL dt minus dir dt equals 0. Maybe I should be explicit here and say this is all for t greater than 0. This 2 is for t greater than 0. And what I want, of course, is from this last expression, I see that dir dt at t equals 0 plus is equal to minus dIL dt at 0 plus, but I know dIL dt at 0 plus which I calculated right above, which was 40 amps per second. So this becomes minus 40 amps. Uh-oh, let's not do it that way. Come on. Minus 40 amps per second. Okay, so that's now my third property. I think I can fit in one more here on this page. So we know the following. We know that next, if you like, next, VR equals I sub R times R, right? Therefore, dVR dt at 0 plus is R times dir dt. Oh, you can now let me erase it. dir dt at 0 plus, and R is 30, and dir dt I just calculated as minus 40, so it's 30 times minus 40, and this is equal to 4 3s are 12, and there are two zeros, so this is sorry, with the minus, let's make that, no, let's do it properly, equals minus 1200 volts per second, and that's property number 4. Okay, let's continue. On the next page, I need two more properties for the derivatives, so let's go on the next page. And again, now I think you'll have to go back and forth between the two pages, but let's look at the center loop mesh. And we had seen that V sub L was equal to V sub C plus V sub R, and therefore dVL dt at 0 plus equals dVC dt at 0 plus dVR dt at 0 plus, and this we know dVC dt, this was 108, and this was 1200, and so I have that this is equal to minus 1092 volts per second. Okay, so this is my fifth derivative, and then I'll now look at the right node. Okay, that right node, you apply KCL, and it says simply that 5 plus IR equals I sub C, and therefore DIC dt at 0 plus equals DIR at 0 plus. And this we've already calculated on the previous page, which was minus 40 amps per second. And so there is my sixth property. All right. So I have now determined the initial conditions for all six properties. Not only the properties themselves, both at 0 minus and 0 plus, but also the derivatives of these properties at 0 plus. Okay? Now it's very important to be able to determine the properties at 0 minus and 0 plus, because the response of a current through a resistor or the voltage across a resistor can change instantaneously. The current through an inductor can't change. The voltage across a capacitor cannot change. But the current and the voltage, the current through and the voltage across a resistor can change instantaneously. And so it's important to be able to determine the initial conditions at 0 minus and 0 plus. Okay? Let's go on from here. The next thing to do is to look at what we call the killed circuit. So let's look at the killed circuit. The killed circuit. The killed circuit, in this problem we only had current sources, so you open circuit the current sources. You open circuit the current sources. Okay. This all falls under the rubric of t greater than 0. And the killed circuit, if you open both current sources on each side, you then have the following. You have an inductor, 3 henries. You have a resistor of 30 ohms. And you have a capacitor of 1/27 farads. Okay? And so immediately you see this is a series RLC circuit. Okay? And therefore, well, next step, determine the frequencies. The frequencies are S1, let me do alpha first. Alpha and omega 0. Well, no, let me do alpha. Alpha, because it's a series RLC circuit, alpha is R over 2L, and this turns out to be 5. And omega 0 turns out to be, which is 1 over root of LC, turns out to be 3. Right? And so you see immediately from here that alpha is greater than omega 0. And so immediately you know that the solution, the response, and let's talk about, let's simply, for the sake of argument, instead of determining all 6 quantities and going on this lecture till tomorrow, let's just consider the voltage across the capacitor. Let's determine the voltage across the capacitor for all time. And so, but going back to this alpha greater than omega 0 means that this is an overdamped response. All right? We know this is an overdamped response. So, let's look at the right side of this page. I know it's an overdamped response, so I can then determine S1, which is equal to minus alpha plus square root of alpha squared minus omega 0 squared to be equal to minus 1, and S2, which is minus alpha minus square root of alpha squared minus omega 0 squared equals minus 9. Okay? And therefore, without any further thought, I can immediately say that the natural response, the natural response, and we are now talking about the capacitor voltage, okay, the voltage across the capacitor. The natural response of VC equals A1, which is A1 e to the S1t, plus A2 e to the S2t, and this is nothing else but A1 e to the power of minus t plus A2 e to the power of minus 9t. Okay, so there's my natural response. What's left? What's left is to determine the forced response. Let me write that down. What's left is the forced response. Okay? For the forced response, so let me write that down. For the forced response, one looks at the circuit as t tends towards infinity. Okay, for t tending towards infinity. But for t tending towards infinity, it's a DC circuit. It's simply a DC circuit. Okay? And so all inductors are shorted, all capacitors are open circuited. And so what does the circuit look like as t tending towards infinity? Well, for t tending towards infinity, the circuit looks like this. There's my good old 4 amp source. The inductor is a short. Okay, then there's my resistor. Okay, there's the resistor of 30 ohms. there's my capacitor, which is open circuited. So this is VC, it's open circuited, and of course on the right hand side I have that 5 amp. Oops. It's the 5 amp source. Okay? Remember, for t tending towards infinity, this is a DC circuit problem, once again. And so, immediately from this, I can determine that VC forced of t is simply equal to 5 times 30, 5 amps times 30, and this is equal to 150 volts. All right, so let me go on to the next page. All right, and let me write down the total solution for the capacitor voltage as a function of time. Again, under the heading for t greater than or equal to 0. All right, and so therefore, or maybe I should write it down here. T equal to 0. Vc of t equals I think I called it A1, e to the power of minus t plus A2, e to the power of minus 9t plus VCF, which is 150 volts. Okay, so that's our general solution, and what's left is to determine A1 and A2. A1 and A2 can be determined by applying the initial conditions. Apply initial conditions. So here we go. Apply initial conditions. Okay, and so we have VC at 0 plus, which we calculated way back then, is 150. And so this is equal to A1 plus A2 plus 150. So this 150 cancels with this 150. And so you have the equation, let me write it this way. You have the equation A1 plus A2 equals 0. All right, so that's one equation. The second equation has to be on the derivative. So let's do dVc dt first. dVc dt is equal to minus A1 e to the power of minus t minus 9 A2 e to the power of minus 9t, and therefore dVc dt at t equals 0 plus is equal to minus A1 minus 9 A2, and then if you recall from the previous page, dVc dt at 0 plus we had determined was 108. Okay, so here are my two equations. This is one equation. This is the second equation. Okay. And if I solve them, I get A1. This leads to A1 equals 13.5, and evidently from the first equation, A2 must equal minus 13.5, and so lo and behold, finally VC of t equals 13.5 e to the power of minus t minus e to the power of minus 9t plus 150, which is the forced solution. And so that is my answer for VC of t. Okay, and so now let's oh, this is obviously for t greater than 0, and I also calculated, if you recall, well, at VC at 0 minus, you also know, is 150. So this is maybe I should say, well, leave it. Let's leave it as that. We know also VC at 0 minus is 150 volts. Okay, okay, so now let's go ahead, and now of course things look very similar to what we did a few lectures ago. So let me, at this stage of the game, let's go and see, let's really complete the problem by going and plotting this function. All right, so I can apply all the original arguments as before. So let's draw this. Well, anyway, I mean, the point is this, that the voltage, if you look at the expression in the box, also this is, you look at the expression in the box, it's at t equals 0 plus, t equals 0, it doesn't matter, this is the voltage across the capacitor. The two exponential functions are 1 minus 1 is 0, so you're left with 150. So and the function is continuous, so we know that at t equals 0, the function is 150 volts. Okay. You also know that the function for t tending towards infinity, okay, is 150, because both the exponentials die down to 0 and you're left with 150. So it's at 150, and ultimately it's going to 150, okay, but somewhere in between, and it's greater than 150 in between, and so there must be some maximum. So let's write down, let's determine that maximum first. So we have VC of t, which is VCN of t plus VCF of t, and since VCF of t is a constant, we have dVC dt equals dVCN only, okay, since VCF is a constant, and this is nothing else but 13.5 minus e to the power of minus t plus 9 e to the power of minus 9t, and this equals 0. And so I have from here a T max. This is trivial. Let me do it over here. Therefore, T max is equal to 1/8 log 9, and this gives me 0.275 seconds. Okay, and therefore we see at T max equals 159.2 volts, and just so that I can actually draw the figure, let me calculate VC at 1 second, and I calculated this to be 155 volts, and VC at 2 seconds, I calculated this as 152. I'm rounding off here, okay, volts. All right, and so let's plot this. Let's plot this. Let me do it over here. And then let me break it here, and I need a little space below. So let's make this 2, 3. This is 0.5. 3. This is 1. 1, 2, 3. This is 2. This is t in seconds. Now I have to be a little careful. Let me go further up here. This is VC of t. VC of t in volts. Let's see. 50, 52, 54, 56, 58. Yeah, it'll work. Hold on. Let me just improve this slightly. Let me break it up there. Okay, so then this I will call 150. This is 152. 154, 156, 158, and is that right? 50? What am I trying to do here? This is 150. Oh, yes. This is 152 here. 152, 54, 156, 158, and 160. Right. Okay. All right. So the function is sitting from minus infinity to 0 minus at 150. Where is it going? it's going to 150. So asymptotically, the function is going to 150. And somewhere in between, it has this maximum. And where's the maximum? The maximum is at 0.275. This is 0.25. 275 is here. This is 0.275. And so let's go up, 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 all the way to 159.2. So this is it. This is 159.2, this point here. And so I know a few other things. I know that at 1 second it's at 155. So this is 155. At 1 second, so this is another point. And at 2 seconds, I know it's 152. So at 2 seconds, oops, come on. 152 at 2 seconds. I have this point over here. So what does my response look like? It goes up, reaches a maximum, and then it decays through that point, all the way to 150 at infinity. All right? And there's just one final thing which is left, which is the determination of the settling time. And so let's determine the settling time. We want the following. We want that, the settling time again. Remember, the e to the power of minus 9t, 13.5 e to the power of minus 9t is dead, long ago, okay? So all we need is the first term in the solution for VC of t, which is 13.5. So we want 13.5 e to the power of minus t settling must equal 1% of the maximum, and so it's 159.2 minus 150 divided by 100, which is equal to 0.092. That's easy. And so we have e to the ts, we have e to the ts equals 13.5 divided by 0.092, which is equal to 146.7, and then this of course then leads to the fact that Ts, which is log 146.7, and this turns out to be 4.99 seconds. So this is the settling time, is 5 seconds. Okay, so way out there is where the response is reduced to 1% of its maximum value. Okay, and so this rather long problem, the point I'm trying to make here is the following. If I said determine the voltage as a function of time across the resistor. You could do that. It's exactly the same procedure, all right? Except that the voltage across the resistor may jump, okay? I could ask you to draw plot the current as a function of time. And again, don't forget, since this is a series RLC circuit, it's an overdamped case, the solutions all look the same. The numbers are slightly different. I mean, the frequencies are not different, but the forced response, etc., may be different, will be different, and so you now know how to tackle a forced RLC circuit and obtain its response for all time. Okay, this concludes the second part of this course. Okay.